So another thing is the model always just tends towards perfect fit as the number of non-redundant regressors approaches n. By non-redundant, I mean the model doesn't do anywhere if you include x and 2x and 4x, right? Those are all just the same variable with a different multiplier. But if you include x and y, and if you have a response y and there's 20 measurements, and you include 20 regressors that are just simulated random noise, then you will achieve perfect fit, even though those regressors have nothing to do with y. R squared increases monotonically as more regressors are included, so the proportion of the variation in the y's explained by the regressors increases monotonically regardless of whether the regressors are important. And the sum of the squares errors decreases monotonically as more regressors are included. So here, just as an example, here's a bunch of simulations for the number of variables included for n equal to 100. And in this case, the way I did it, so this is a different set of simulated data for each number of regressors. That's why it's all kind of bouncy like this. So no actual regression relationship exists in any simulation, right? So you can just see I'm just putting random noise into a regressor, into a response, and you see as you get up toward 100, you're guaranteed to get 100% of the variation explained in the y's. So let's look at variance inflation, and like I said, this is a statement about the true standard errors. So I'm going to do a simulation to look at the true standard errors. So my n is 100, and I'm going to do 1,000 simulations, but you can bump that up to 10,000 if you want the Monte Carlo variation to be small. Okay, here's our three regressors, x1, x2, x3, and then what I'm going to do is I'm going to get a bunch of things called betas. And that I'm just going to grab the coefficient for x1 from every linear model fit, and I'm going to do it number of simulations times. And what I'm going to do is I'm going to fit the y given x1 and regression model, and then I'm going to add random noise. So this simulation part of it is adding random noise a bunch of times, 1,000 times, and then I'm just going to so that's how I generate my y, and then I'm just going to fit three regression models, one that includes only x1, one that includes x1 and x2, and one that includes x1, x2, and x3, and in each case I'm going to grab the coefficient for x1, and then I'm going to, so what have I done? I've repeatedly simulated from the regression model, and I've gotten the beta 1 coefficient. And so I'm going to look at that distribution, and the standard deviation of that distribution is the population standard error of beta 1. Okay? And what you can see is in the first case where we only have x1, we get a standard error of 0.028. Then it goes up a little bit higher, 0.02872 if we include x2 in the model, and then it goes up even a little bit higher if we include x3 in the model. That's variance. That's the variance inflation. But you can make the invariance inflation much worse if here's our x1, which is a normal, but now instead of x2 being just another random normal, I made x2 a average of some random normals and x1 a kind of average. And I did it so that kind of how related to x1 it was. In this case, it's I think I did it by square root 2 so that the variance of x2 remained 1. In this case now, the variance of x3 is also 1, but x3 is highly related to x1, right? It's sort of 95% x1 and a lot less of percent x2. So then I just did the same thing, and now you can see for x1, here's my standard error estimated by simulation. If I include x2, right, if I include x2, which is not related to y, right, I get a small amount of variance inflation, and then I get a huge amount of variance inflation. My standard error from the original goes up 3 times by including x3, which, as we note, is highly related to x1. So the more correlated your regressors are, the more variance inflation you're going to see. So there is these things called that look at this called variance inflation factors. And I just want to highlight this point. Notice variance inflation was much worse when we included a variable that was highly related to x1. And then, we don't actually know sigma, so we can only estimate the increase in the standard error of the coefficients for including a regressor. So when we take ratios, the sigma drops out. So we can actually calculate the percent increase or decrease in variation explained by including an extra regressor. So when the regressors are orthogonal to the regression or regressor of interest, there is no variance inflation. So what they define something called the variance inflation factor, which is the increase in the variance for the ith regressor compared to the ideal setting where it's orthogonal to all the other regressors. And the square root of the variance inflation is the increase in the standard deviation instead of the increase in the variance. And then I just want to say, remember, variance inflation is only part of the picture. We may even want to include a variable even if it inflates the variance of our variable of interest, because it's important. It's an important thing to adjust for. So let's revisit our previous simulation. But notice, let me just say something. Remember, in our simulation, there was 3 things. There was y, x1, x2, and x3, and we simulated a new y x every time, but our x1, x2, and x3 were constant at their original value, and then we added, I guess we simulated errors each time. So what we're going to talk about actually doesn't depend on either y or the errors. It only depends on x1, x2, and x3. So you can calculate this for any given problem. So say we're interested in variable x1, and what's the consequence to the real standard error for including x2 versus including x3 in terms of the true standard errors expressed as a ratio of the standard errors. So this summary of this linear model fit, if you grab the unscaled covariance, the 2,2 entry is this variance for beta 1 in this case. And that's maybe a bit detailed, but it's true, so just trust me on that if you don't quite get that. But so what I'm doing in each of these cases is getting the standard error sigma beta 1 hat, which involves sigma hat, divided by some function of the x's. Okay, and so we're going to take ratios. This sigma hat will drop out, so the fact that we estimated sigma hat won't matter. Okay, and from that we can see the variance inflation, and so here I divide the variance, the variance of the coefficient in front of x1. I divide the standard error for that coefficient, the variance for that coefficient, by what we get if we only include x1 to if we include x2, and what we get if we include x3. See, I divided it by a, where I defined a up here. Okay, so what this means is we get a 90% increase in variation from the model that only includes x1 by including x2, and we get a 9-fold increase in variation by including x3, and that's exactly what we saw in the simulation. But notice these are things we can do in our actual data. We don't need a simulation. Okay, and in fact, I can show you, via the simulated data, if I were to just take my simulated betas and calculate the variance, right, and get the variance for if I just have x1, if I have x2, and if I have x3 included, x2 and x3 included, and I take those the variances for if I include x2 and x3, and I divide it by the variance if I only have x1, I get the numbers that are very similar, and if I were to simulate enough, I would get exactly the same numbers as these.